So right now I'm doing a screencast of all the worksheets I've completed, which will include an explanation of how I got my result and the reasoning for it. So first off, we're going to look at worksheet NT5B-QRT27, which is the three vectors and resultant. So for this one, first I did a triangle shape to add the vectors and get a resultant of R. But actually the better, most effective method is to draw a four-sided figure. That way you have your three vectors and the resultant vector, which is sigma f, or the resultant vector, which is the sum of all the forces. And yeah, that's a representation. I also noted there was a connection between the net force and acceleration, just for future reference. Okay, for part B, I've said that David is pulling northwest because you have Abel pulling to the right, you have Cecilia pulling southwest, and you have Beth pulling southeast. So you need a fourth vector such that the net force equals 0, and that would be David. So David would be pulling northwest. Now the next worksheet is NT5B-RT10, which is the blocks floating in liquids, or force exerted by liquid. Okay, so there's 6 figures which show 6 identical blocks in 6 different liquids. That's a key phrase. Same volume in all 6 containers, but the masses vary. Okay, most of that is all like mumbo jumbo, but we need to focus on 6 different liquids. So therefore the force exerted by the liquids is the same for all these liquids because the blocks are identical. So you have to pay attention to your key phrases rather than your mumbo jumbo that you're given. Now the next worksheet is NT5B-CC1019, block moving at constant speed, forces on block. Okay. For this one I put Barb is right because she states that the weight is definitely greater than the normal force. As you can see here in this diagram, the weight is greater than the normal force. So we're paying attention to only the highlighted words, which is pull a block across the table at a constant speed. So Barb said, well, the weight is definitely greater than the normal force, which is obvious here. But there should be a net force to the right in the vector sum because that's the way the block is moving, which is true because you have a force on this side, you should have a force on the opposite side. And there isn't. I don't think we can use it to rank the other forces, which is very true. Now the second sentence of Anja's reasoning is not reasonable. And for Cole, he's just stating a bunch of assumptions that we don't even know. Now, moving on to elevators. This is worksheet NT5E-CT49. Person in an elevator moving upward. Okay, so in 2 cases, person is studying an elevator. Okay, so we have 2 identical elevators. Person weighs 500 newtons. Elevator is moving upward, but in case A, it is accelerating upward. Okay, that does not matter. If it is accelerating upward or downward. Will the scale reading in case A be greater than, less than, or the same as? I think same because the normal force is the same in both situations. As you can see here, the sum of the vectors is this, and the normal force is up. This is the weight, this This is the normal force. This is the weight. Normal force is scale reading. Yeah. Okay. Now we have the same thing moving downwards, but it's still going to be the exact same situation. But I accidentally wrote, I forgot to cross my answer out. But I initially said case A is greater than case B because it's accelerating upwards, so it's speeding up. But that was before I learned that it should be the same because the normal force is the same in both directions. Yeah, velocity does not matter. So that was a big concept. See, the force diagram here is the same here, or the vector diagram. Here, same here. You add the vectors to see where acceleration is going. Moving spaceships. Okay. Both cases, moving spaceship connected to two cargo pods. Let's see, skip the mumbo jumbo. Speed is constant at 300 meters per second. For a case A, case B, it's 500 meters per second. Both speeds are constant, all masses. Okay. So what we really need to know is that they are constant speeds. And I put the magnitude of the tension in all the rods is the same but not zero. Cannot be zero, but it's obviously the same because they are going at constant speeds. That's why the magnitude would never be zero, I believe. The ranking for the tensions in the rods cannot be determined. No, that's false. So the magnitude of the tension in all the rods is the same but not zero. For which you can make an educated guess even. Now with 4 cargo pods. Constant velocity. Velocity is actually 5,000 meters per second. And this is actually all we would need to know. And this is basically, I think, the same as the other problem. So I had put the magnitude of the tension in all the rods is the same but not zero. Because they're going at a constant velocity. So now let's see, student pushing 2 blocks. Okay. Student pushes horizontally on 2 blocks. Blocks are moving to the right. Block A has more mass than block B, and there's friction. Okay. So I highlighted constant speed because that was what most important to me. And that's why I put the force that block A exerts on block B is equal to the force that block B exerts on block A. Number 2. The situation where the blocks are moving at a constant speed, which of the following is true about the net force? Net force on block A points to the right and is equal to net force on block B. And that is true due to not only friction, but the constant speed and the magnitude of forces. Yeah. Number 3. For the situation where the blocks are slowing down, which of the following statements is true? Even if it's slowing down, the force that block A exerts on block B is equal to the force that block B exerts on block A, by all means. Because the force shouldn't change, even though they're slowing down. Number 4. For situations where the blocks are slowing down, which of the following statements is true about the net force? The net force on block A points to the right and is equal to the net force on block B. Okay, the net forces must be the same. Actually, they must equal 0. And that is because A and B, even though they have different masses, exert the same force on each other. Okay. Now the tugboats. Okay, tugboats pushing barges. Okay, in each one, tugboat is pushing 2 barges. they are all accelerating at different rates. Accelerations are given, and the positive direction is to the right, and the rest is just unnecessary. Once again, I put the force that the tugboats exert on the barge, on barge 2, is the same but not 0 for all the systems. Now, the reason for that is because the tugboats cannot exert a force. The tugboat's force could not equal to 0, so there must be a force. We also cannot determine the rankings for the forces, but our best bet would be that the force exerted on barge 2 is the same but not 0 for all the systems, and that is because the acceleration, which has an interaction with net force, are all pretty much the same. So that means the net force is the same, which means they all the systems exert the same force, but not equal to 0. Now, for velocity versus time graphs, we have these graphs below show the velocity versus time graph for two identical train engines. And that's all we need to know. The student is asked how the net force acting on the engine in graph A as the identified point compares to the net force acting on the engine in graph B. He says, I think that B has a larger net force since the net force on A at the identified point is 0. What is wrong with this statement? If anything, identify it. I put it's wrong because they both have the same net force, because both acceleration equals 0. So constant acceleration equals 0 net force, which goes for both the graphs. And that is because of the law that acceleration equals 0, net force equals 0. For this worksheet, NT5BCT21, blocks moving at constant speed, force on block. In both cases shown, a block is moving to the right across a rough table which has friction with constant speed of 2 meters per second. Tables are the same, and the angle theta that applied the force makes with the horizontal is the same in both cases. Will the magnitude of the force on the block by the stick in case A be greater than, less than, or equal to the tension on the block by the string in case B? I put equal tension, not only because the tables and blocks are identical, because they have a constant speed of 2 meters per second, and the angle applied is the same for both cases. And just to have a quick, just to tell you what worksheets I did, let's go in order. The first one, 3 vectors, resultant NT5B-QRT27. Number 2, NT5B-RT10, which is the blocks floating in liquids. Next one, NT5B-CCT19, block moving at constant speed. Elevator, NT5E-CT49. Moving spaceships with 2 cargo pods. NT5A-RT3. Moving spaceships with 4 cargo pods. NT5A-RT1. Student pushing 2 blocks. NT5B-QRT12. Tugboats. NT5B-RT5. And velocity versus time graphs. NT5B-WWT20. And that's all for my screencast.